an plus plus is uniquely assigned to n plus plus. This completes the induction and proves the proposition. Here the proof ends, and the fact that we have used the fifth axiom is simply indicated by the way we have proved it. We are using induction means we are using the fifth axiom. Now, just out of nowhere, why have I decided to define sequences inductively or recursively? And what will it give me? What shall I achieve by doing this? And what is the relationship of this thing to the axioms that we have had so far? The thing is that this is a very powerful principle of recursive definition. It can be, I have already said in the previous part, it can be used to define addition and multiplication of natural numbers. And we will do that now. Okay. We will actually define what addition means, what multiplication means, and we will prove all the known laws of arithmetic that we are so familiar with. So to that we will now turn. One more thing that before ending this section, so this is the last part of the section 2.1, you can see that in this scheme of defining the sequence, A naught, etc. If my number system has a superfluous element or some superfluous element, some rogue elements, if you remember, we had a number system which looked like this. It had, apart from the usual natural numbers, it had half integers. So in such a system, if I apply my principle of recursive definition, terms like a.5 will never be defined. Okay, so that's why principle of recursive definition applies only to sequences, not things like this. Now we start our second section of the second chapter. Okay, so the second section is, this is 2.2. The title is addition. Okay, so the natural number system that we have right now is very bare. It only has a set, the natural numbers, and it has an incrementation operation. So this is the system. And besides that, we are yet to see what sets are formally. Okay, so that is still there. We don't have anything else in this system, but now we are going to rectify the situation, and we are going to introduce our first actual complex operation, more complex than this primitive incrementation. That is, we are going to introduce addition. And here's how it is defined. In defining this operation, we will need the principle of recursive definition. That's why we have done this thing. And the proof that we have carried out justifies that such a thing actually gives me a legitimate definition. And this is definition 2, so I have to follow the numbering also. Two, two, one. And its name is addition of natural numbers. So what it says, let M be a natural number. M is any natural number, okay. To add 0 to M, we define zero plus M equal to, okay, keep this colon in mind. The meaning of 0 plus M is nothing but M. When I write 0 plus M, that just simply means M. So this is another, this symbol is just another way of writing M. That's all. That is the definition. But this is just only one value, right? We have to define N plus M, where N can take any value, and this is where we are using the principle of recursive definition. Suppose we have defined N plus M, where N is some natural number. Let me write that also, where N is some natural number. Then what is the meaning of this that I have to say? What does it mean to add the successor of N to M? That I am defining to be equal to N plus M, its successor. Okay, watch this carefully. What I have done, I have defined 0 plus M, which is equal to M. And suppose I have defined N plus M, where N is some natural number. Then the successor of N plus M is defined to be equal to the successor of N plus M. Now, exactly how have I used the principle of recursive definition? What is Fn here? What are the functions Fn here? And what is C here, by the way? So for me, if you look at this and compare this with this An plus plus equal to Fnan, okay, then we get these things. An actually has to be equal to N plus M. Remember, M has been chosen by us. M is arbitrary but fixed. M is not changing. We are changing N. This is one thing. And Fn x, because Fn is a function from the natural numbers into the natural numbers. Fn x is equal to, so these things I am defining, okay, is equal to the successor of x. Does it make sense? If I put a natural number x here, what this function does, it gives me the successor of that natural number. And this is a case where you see that these functions are all the same. Okay, f0, f1, f2, f3, all of them are this functionality, the incrementation function. Actually here, the incrementation function has been written in functional form. Okay. So, do we really get this from here? If I write, you can see here, what is an plus plus? If I use this formula, an plus plus is, in place of n I have to use n plus plus. An plus plus is n plus 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 m. This is the left hand side. And what is the right hand side? The right hand side is fn n plus m. See, fnx is the successor of x. So fn n plus m is the successor of n plus m. And what is n plus m? An. So that's how I have used the principle of recursive definition here with these things. An, the meaning of an here is n plus m, and the functions fn are all equal, and all of them are equal to the incrementation operation. So that means my definition is legitimate. This definition will give me a single value to n plus m for a given m. And since m is arbitrary but fixed, I can change the value of m. So this is how I have achieved the definition of addition. Okay. But I have achieved the definition means I have simply defined something. Now I have to see whether this is legitimate addition or not. And note that the fact that this definition is actually defining the sum of any two natural numbers is guaranteed by the principle of recursive definition, which we have proved. Without which we cannot define it. I mean, we can, but then we will have no way of saying that it legitimately defines something. Okay. So let us now just start by looking at some consequences of this definition. 0 plus m, by definition this is equal to m, which is okay. This matches with what we know about natural numbers. What is 1 plus m? What is 1? 1 is the successor of 0. Now if I use this means it should be the successor by definition, okay? 0 plus m. And 0 plus m is what? I already have it here. So 0 plus m is m, so 1 plus m is the successor of m. So you see that I have at least got something the way I want to have it. The way I was defining natural numbers was this, right? Now if I put m equal to 0, I have 0. If I put m equal to 0 here, I have 0 plus plus. That is because of this formula, I have this identity. What does this tell me? It tells me that the successor of 0 is actually 1 plus 0. So I get the successor of 0 by adding 1 to 0. That's what we already know. But since addition was not available to me, now only it has become available. So we took the help of this more primitive function, incrementation, to define the system. And now after having defined it and having defined addition in terms of everything else, it turns out to be true that my previous knowledge of addition is matching with this framework. Okay, so far it's okay. Let's calculate one more. What is 2 plus m? 2 plus m is, 2 is the successor of 1 plus m. So proceeding in the same way using this definition here, I get 1 plus m plus plus. But what is 1 plus m? 1 plus m is the successor of m. So this is the successor of m and its successor. So it's matching. You see m, 1 plus m is the successor of m. 2 plus m, or I should write like this. The successor of the successor is 2 plus m. So incrementing 2 times. You recall, adding 1 to m means incrementing m once. Adding 2 to m means incrementing m twice. So they are matching. So far it's okay. But these are just some preliminary considerations. Right. So now instead of having n and m, if I say have 2 plus 3, 2 plus 3, just now I have found it. 2 plus 3 is what? The successor of 3 and its successor. So the successor of 3 is 4, whose successor is 5. So that's how I am getting the addition. Okay, now one more point about this definition. The definition of addition is asymmetric asymmetric in what sense? 3 plus 5 is obtained by incrementing 5 3 times, while 5 plus 3 is obtained by incrementing 3 5 times. Okay, by definition we get this 3 plus 5. If we extend these calculations, I mean we can do this, right? We can calculate 3 plus m, which will be 2 plus m. So using this definition it will be 2 plus m plus. And we have already found out the expression for 2 plus m, which is nothing but the successor of the successor of m and its successor. So adding 3 to m means incrementing m 3 times, once, twice, thrice. So adding 3 to 5 means incrementing 5 3 times. You can see that if we extend this, then 5 plus m will be this. You increment once, twice, 3 times, 4 times, 5 times. Okay. Now, if I just simply use these expressions to write these two things, 3 plus 5 is 5, 1, 2, 3. But 5 plus 3 is 3, 1, 2, 3, 4, 5. Do they look the same? I mean, you can of course show that they are same in this case, but what about in general? I mean, just looking at the expressions, who knows if they are same or not? Simply from the definition, we cannot say that 3 plus 5 is equal to 5 plus 3, not so fast. It's not obvious from the definition that 3 plus 5 should be equal to 5 plus 3. It will turn out to be equal to, I mean, they will turn out to be equal, but that has to be proved. In that sense, this definition is asymmetric. It's not symmetry. We don't immediately get from the definition that n plus m has to be equal to m plus n. This has to be proved. Without a proof, we can't say, because you see, who will say that these two things are equal just by looking at them, without thinking of them anymore? And if more, I mean, higher numbers are involved, the situation will be more complicated, in the sense that many more incrementation operations will be there. So we don't know yet that this is the case. This we will prove, and this is the first major result in this whole thing that we will prove. You already know what this is. This is known as the law that addition is commutative. So we are now going to prove this one. We are going towards that. But before we prove the actual commutativity, we have to go through some preliminary lemmas. But before we go to even that, there is one more fundamental question. And that question is, it has been asked in the text as a why. So I have created this why exercise. There are many why exercises that will come as we progress further. So this is the first why exercise of this section. Y is the sum of 2O, by the way, I should have said this now. In the definition 2 to 1, you insert one more line. N plus M is called the sum of N and M. This extra line you add to the definition of addition of natural numbers. Y is the sum of two natural numbers, again a natural number. These things are taken for granted, but they nonetheless have to be proved. We have defined a sum using recursive definition, but what is the guarantee that n plus m is always a natural number? Because otherwise we are going outside the system, no? You see, for example, let's digress for a little bit and think of, instead of addition, let's think of subtraction. Instead of addition, we are thinking of subtraction. If we use the operation of subtraction that we already know, okay, from our prior knowledge, then things are not that smooth with subtraction. 2 minus 1 is okay, it is 1. but 1 minus 2 minus 1. We are no longer in the system of natural numbers. So it has to be proved that the sum of two natural numbers is a natural number. And this is also not obvious from the definition. It has to be proved. The proof is very easy, but the proof is necessary. So since it has been given to us as an exercise, so it will be a solution. To prove this, we prove n plus m is a natural number for any two natural numbers n comma m by induction on n keeping m fixed. So we are going to keep m fixed. M will be any natural number, arbitrary but fixed natural number, and we are going to prove this claim by induction on n. So the value of n we will change. 0 plus m is equal to m, which is a natural number. So when n is equal to 0, then n plus m is a natural number. Suppose or assume same thing, n plus m is a natural number for some natural number n. You may have noticed one thing. I am having to write natural numbers again and again. Isn't it better to write for some, instead of writing for some natural number, I can write for some n belonging to n. You see how neat this is. I don't have to keep on writing these words. But we are not doing that here because we are trying to avoid set theory. We have not presented them to you. Axiomatic set theory. So that's why we are avoiding writing that notation. So suppose n plus m is natural number. So this is my basis for the induction. Then this is my induction hypothesis. Now I have to prove or carry out the induction step. Then n plus m equal to, see, by definition this is the successor of n plus m, is a natural number. Why? From here, how can I conclude that this is a natural number? It becomes a natural number because of two things. By the induction hypothesis, what is my induction hypothesis? That n plus m is a natural number. So the number inside the round brackets, this is a natural number. And axiom 2.2. See, the axioms are still playing a role. What does the second axiom say? when we have a natural number, its successor is also a natural number. So this is the successor of n plus m. N plus m is natural by the induction hypothesis. Its successor is natural by the second Peano axiom. And this completes the induction. This completes the induction, and now the proof is over. Now we can say without any doubt that whenever we add two natural numbers, the result is always a natural number. Okay. So now we are going to go to some lemmas that will eventually take me towards commutativity. The proofs of these lemmas and the statements also are not very difficult, but nonetheless they are important. For any natural number n, n plus 0 is equal to n. See, it looks obvious, but it's not obvious. What does the definition say? The definition says that for any m, 0 plus m is equal to m. But what about m plus 0? That using the definition, we immediately don't get anything. I don't really know what m plus 0 is, just from the definition. We have to prove that it is equal to m, or in this case, it is equal to n. And the proof, invariably all the proofs now will go by induction. So the fifth axiom, so that's why I said that the fifth axiom of Peano is really the heart of all the things. It gets us started. Without it, we are nowhere. We can't even take the first step. The proof is very easy. When there is only one variable involved, you can start the proof by saying we apply induction. But when there is more than one variable involved, you have to explicitly say on which one you are applying the induction and which one you are keeping fixed. And in some pretty complicated proof that we will come across at one point, we may have to apply induction on both. We will see those things later. Okay. So here we simply write we apply induction on n, that is understood because n is the only variable here. By definition, zero plus zero. See, I have to show this. So when n is equal to 0, then 0 plus 0 is equal to 0. And this I am getting from definition. What does the definition say? The definition says 0 plus m is equal to m. So in the definition, I have taken m equal to 0. That's it. That has given me this. So the result is true for n equal to 0. Now we assume the induction hypothesis. Assume n plus 0 is equal to n for some natural number n. Then n plus 0. Okay, I have to show that this is equal to n plus plus. But I have my definition with me, definition of addition. By that definition, this is equal to n plus 0 plus plus, successor of n plus 0. Now, by my induction hypothesis, n plus 0 is equal to n. So, in place of n plus 0, I can write n, and the successor is there. So, that's what I wanted to show. This plus 0 is equal to this. This completes the induction. And the proof is over. So now I not only have 0 plus something equal to that thing, but I also have something plus 0 equal to that thing. Along the same lines, I next have this one, lemma 2 to 3. For any natural numbers n and m, n plus m plus plus is equal to n plus m its successor. Okay, this is different from the definition. What the definition says, n plus 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 m is equal to the successor of n plus m. So that means the definition does not immediately tell me that this is also true. I have to prove this. Here also the proof goes by induction, but since two variables are involved, I have to mention on which one I am applying induction.